Today we'll consider this question 2 on linear algebra from Gunning's An Introduction to Analysis. It reads as follows. Find a basis for the subspace of R4 spanned by the vectors 1, 2, minus 1, 0, 4, 8, minus 4, minus 3, 0, 1, 3, 4, and 2, 5, 1, 4. Take a couple seconds to try this out for yourself, then we'll do some hints, then we'll get on with the proof. Alright, so for our hints, we'll first note that that it'll be useful to recall what the definition of a basis is for any subspace, and then we'll recall it might be useful to figure out what the definition of linearly independent means. Alrighty then, let's begin. So for this problem, we'll first note, let's do some notations, which is, let's call this U, let's call this V, let's call this W, and let's call this last one Y. That'll make it useful in the future. And so the idea is that to find a basis of a subspace spanned by these elements, we first need to note that a basis is the minimal spanning set in the sense that you need the fewest number, and in the sense that they need to be linearly independent from one another. So we clearly see that this set will span it, but it's not necessarily a basis, so we need to check if it's a basis. In particular, let's check if there's any way to write one as a linear combination of the others. This is just a personal preference, but let's try to solve for y in terms of the others. So we're going to try to solve for this equation, where alpha u plus beta v plus gamma w equals y. If we can find a solution to this that is non-zero, or if we find a solution to this equation, we see that we'll find a solution to the zero equation, so therefore they will not be linearly independent. So with this, we see that we can actually generate some equations. In particular, for each line of this, we can generate some equations. So let's start with the last line. Namely, we'll see that if we look at the last element of each of these, we get a particularly nice equation of 0 alpha plus minus 3 beta plus 4 gamma is supposed to be equal to 4. And clearly check that this implies that gamma can be written as is equal to plus 1 plus 3/4 beta. So with that, we have one way of writing gamma in terms of beta. So let's look at another equation. Namely, let's look at the first line, and we get the equation alpha plus 4 beta plus 2 gamma equals 0. If you plug in our definition of gamma, this implies that we can write alpha as minus 2 minus 5.5 beta. Now I have two equations relating gamma and alpha to beta, so we can solve for beta. And let's use the second line, which will tell us we have that 2 alpha plus 8 beta plus 5 gamma equals 3. You can check that this implies that beta is equal to 8 over 3. Once you have beta is equal to 8 over 3, you can solve back for alpha and gamma, and you see that y can be written as a linear combination of u, v, and w. Therefore, this is not linearly independent, so it cannot be a basis. So we're down to the set of u, v, w. So for instance, let's try alpha u plus beta v equals w. If this were true, then they would still be linearly dependent, and you'd have nothing more you can do. But you can check this fairly quickly that this is impossible. For instance, we need u plus v is equal to w, so we need alpha plus 4 beta equals to 2, and you need simultaneously that 2 alpha plus 8 beta is equal to 5. by from the second line. But these, pretty clearly, are parallel lines, so they will never intersect. Therefore, there will be no solution for alpha and beta at the same time. So there are no solutions for this. Therefore, you cannot write this expression, and therefore you cannot rearrange the expression anyway. So these are linearly independent. So you have a linearly independent set that still spans it, since anything in the space that's spanned by these four elements can be written in terms of just u, v, and w by taking however many copies of y you need in your original representation and replacing it with alpha u plus beta v plus gamma w copies of that element y. Or of y. Replace this left side for y in your representation that you originally had in the spanning space. Therefore, your u, v, w spans this entire space, and they're linearly independent, therefore they serve as a basis, so you're done. So your basis is this vector, and this vector. With that, thank you for watching.